Hello dear students. In the previous video we discussed the dangers of electricity. In this last video we will finalize this chapter and discuss the last objective, which is identify the role of safety devices that protect from electrical hazard. So how is protection against electrical hazards attained? In fact, through switching off devices. We will talk about 3 switching off devices, which are fuse, circuit breaker, and differential circuit breaker. Let's begin with the first one, which is the fuse. In this activity, we have a fuse in a circuit. The fuse protects the lamp from short circuit. But how does the fuse work? Let's observe the parts of the fuse before we discuss how it works. The fuse has 2 metal ends and a main part inside, which is a thin fuse wire. This thin fuse wire can withstand a certain amount of current. What happens if the current exceeds this amount? The fuse melts if too much current flows inside it. So in this case, the filament or the strip inside will be broken and the circuit is opened. Thus, the appliances are protected. So to summarize, the fuse is a thin metallic strip that can withstand a certain amount of current. It is connected in series to the device along the lifeline, and it protects devices against excessive currents. Now let's talk about the second switching off device, which is the circuit breaker. The circuit breaker is installed in a domestic installation between the electric meter and the electric devices, which are connected in parallel. When is a circuit breaker released? Here in this video, you can see when we have many electric appliances running together and the current exceeds the one supported by the circuit breaker will be released to protect against this excessive current. The circuit breaker protects the houses also against short circuit. Let's watch this video to check how. Here we have a short circuit that might lead to fire in the house. This happens in the absence of a circuit breaker. But the scenario is different in the presence of a circuit breaker. Let's watch what happens. Here, the same short circuit happens, but the circuit breaker will be released and no fire takes place. Now to summarize, a circuit breaker is connected in series to the installation on the lifeline. It protects the installation against fire in the case of short circuit or overloading. Finally, let's talk about the differential circuit breaker. In this figure, we have a differential circuit breaker. The black line represents the live line, which carries 10 amperes current. And this is a person touching accidentally the live line. Thus, we have a current, an amount of current leaking. Due to this leading current, the amount of current passing back through the neutral line will be less than 10 amperes. The differential circuit breaker will detect this difference between the live line and the neutral line, and it will be released, thus protecting this person from electrocution. Well, the differential circuit breaker is connected in parallel to the mains on the live and in neutral, and not in series like the circuit breaker and the fuse. It cuts off the circuit when a person touches accidentally the live terminals. It protects the person against electrocution. Now let's move to solve exercises as an application. We will solve two book exercises. The first one is exercise 12. Let's read it together. If the current in the table below exceeds the value corresponding to the cross-section, a fire may start. Let's observe this table. It shows the section of wire in millimeters squared and the current admitted in this wire in ampere. When the section of the wire is 1.5 millimeters squared, the current allowed or admitted in the wire is 10 amperes. This means that it can carry up to 10 amperes without having fire. When the section increases, the current increases, as we can see in this table. Specify the risks in the following cases. When connecting to an outlet wires of 6 millimeters squared, the maximum current allowed in the fuse is 10 amperes. Here we have the wire cross-section is 6 millimeters squared. According to the table, it can carry 32 ampere current, which is more than that of the fuse. So, if current more than 10 amperes crosses, the fuse melts and the circuit will be open, then the wire will not be overloaded. Thus, in this case, there is no risk of fire. Now let's move to solve part B. We want to specify the risk when connecting an outlet by means of wires of cross-section 1.5 millimeters squared and a fuse that is marked 32 amperes. According to the table, if the wire section is 1.5 millimeters squared, it can carry up to 10 amperes without having a risk. This value is less than that of the fuse, but the fuse can withstand 32 amperes. Then for the fuse to melt, more than 32 ampere should cross the wire, hence the wire can be overloaded. Thus, there is risk of fire. So as a remark, we can say that to protect the appliance or the wire, the current supported by the fuse should be less or approximately equal to that of the appliance or wire. Finally, let's solve exercise 14 together. In household installations, the circuit breaker can support a maximum current of 30 amperes. We need 2 ampere for lighting, 10 ampere for an electric oven, 7 ampere for a radiator, and there are 4 of them, 5 ampere for heating water, 3 ampere for cooling. The question is, can all these appliances function together without causing a release of the circuit breaker? Here the appliances are connected in parallel, so according to the law of addition of current in parallel connection, the current is additive, so the main current is equal to the sum of all the currents of these appliances, which is 2 plus 10 plus 7 times 4 because we have 4 radiators, plus 5 ampere plus 3 ampere, so the total will be 48 ampere. Now we will compare this main current value to the one supported by the circuit breaker, so it is more than the maximum current supported by the circuit breaker, so the circuit breaker will be released and the appliances will not function together. Now let's move to solve part B, which is the last one. In summer, we do not need the heat radiators. Can all the other appliances function together? If in summer the radiators are not functioning, then we will not add the current carried by them. So the current carried by the other appliances is the sum of 2 plus 10 plus 5 plus 3 without taking into consideration the 7 ampere times 4. The total will be 20 ampere. We compare this value to the maximum current supported by the circuit breaker. It is less, so in this case all the appliances can function together.